welcome to Optimization Tutorial 11, Optimizing Neural Network. So what is a neural network? As we have seen, a neural network is a function with some constants that are called weights and biases. This function takes an input and spits out an output after doing some operations on the input using the weights and biases. The neural network is built from layers. There are three kinds of layers. There's an input layer, an output layer, and hidden layers. Each hidden layer and the output layer will get as input the output from the previous or some previous layers. Usually between the layers, there is a squeezification function as ReLU or tanh. This will limit the activation of the neurons to some desired range. This will prevent the weights and biases from getting too big and causing numerical issues. The goal in training a neural network is finding the right weights and biases to give the desired output for given inputs. Here we can see a basic architecture of a neural network. There's an input layer, some hidden layers, and an output layer. And here we can see the squeezification functions. The ReLU function limit the activation level of the neurons to be only the positive numbers. And the tanh function limits the activation range of the neurons to be between -1 and. So let's use optimization methods to find these weights and biases. So for that, we need to define an optimization problem. So given a set of inputs with corresponding outputs, let's call them xi and yi, the optimization problem will be the wi and bi, those are the weights and the biases, would be the weights and biases that minimize the average cost function over applying the neural network using the weights and biases on the inputs and comparing them with the outputs. So C is the cost function to minimize. It could be MSE, it could be L1 norm, it could be regularized, it could be constrained, it could be anything you want, which will represent for us the error of the neural network. Phi is the function that the neural network dictates using the weights and the biases wi and bi. So the goal, to find the minimal point of the cost function. So because the neural network contains usually many variables, using methods that use the Hessian is not practical. So another problem with optimizing a neural network, the dataset is very big, and computing the gradient on all the data at each step would be very expensive and will take way too long. So for that we have stochastic algorithm. A stochastic algorithm will not look on all the data and will not pick the necessarily best direction to use, but it will have shorter computation time per step and will converge much faster than an algorithm that will pick the perfect direction to use each time, but each step would take much longer. So stochastic gradient descent is as follows. Divide the data to batches. For every epoch, compute the gradient for each batch and make a step in the inverse direction of the gradient. If the batch size is 1, then the algorithm is fully stochastic. An algorithm is called stochastic if it does not use the entire data it has to decide what is the next step. Note that even if the stochastic algorithm will need more iteration to find the optimal point, each step will be done much faster, as we do not need to look on the entire dataset. So here we can see an example of using a batch gradient descent, which uses a batch number that is larger than 1 or maybe the entire dataset, and here we can see the stochastic gradient descent. So you can see how it goes relatively straight to the optimal point using batch gradient descent, and it's very unorganized and maybe a tiny bit drunk looking using stochastic gradient descent. So this method looks much more messy and less efficient, but each step here takes much longer than each step in this algorithm. So the zigzag of the gradient. A problem with using gradient descent algorithm is that the gradients in each step will be almost orthogonal to the ones in the previous step. So why do we zigzag? As we can see, we would not converge as fast as possible because in each step the gradient would zigzag and waste time instead of taking a step in the actual optimal direction. So why do we zigzag? Let's think what would happen if we would use gradient descent with the entire dataset and use exact line search to find the step size at each iteration. So at point xi, we will calculate the gradient at point xi and do a step in minus gradient direction. with the optimal step size alpha that we got using line search. We got to point xi plus 1. Then at point xi plus 1, if we do a step in the direction of minus the gradient at point xi, then we cannot get a point lower than xi plus 1. This is because we did an exact line search. Assuming that the step in direction minus the gradient of xi in point xi plus 1 with step size beta will lead to a better point, meaning with a lower values than xi plus 1, we get that step from xi in direction of minus gradient with step size of alpha plus beta will be better than just alpha, in contradiction to the optimality of alpha, which we got using exact line search. And so, because alpha is optimal, we know that minus the gradient at location xi plus 1 is completely orthogonal of the minus gradient at location xi. But we don't use stochastic gradient descent, we will not use exact line search, and we will not get a completely orthogonal direction. And we also don't use the entire data set. And so the zigzags will not be completely orthogonal, but the problem stays, as the functions using different parts of the data would be very similar. And alpha, if we pick it correctly to be not too bad, it would be some part of the optimal, and so it would be very close to the optimal step size. And so the casting of minus gradient of xi on minus gradient of xi plus 1 would be very, very low, leading to almost orthogonal directions. So how can we improve stochastic gradient descent? There are a few algorithms that will try to overcome that problem. The first one is called momentum. So the direction iteration k equals to 1 minus beta, the iteration at the direction at iteration k minus 1, minus beta multiplied by the gradient at point k for some beta between 0 and 1 that is constant and an hyperparameter of the algorithm. xk plus 1 is equal to xk plus alpha vk. So we added to the step direction the direction from the previous iteration. Alpha is the step size and beta is the hyperparameter of the algorithm. This will try to prevent the zigzag of the direction by adding the previous direction, because we know that the new gradient will be almost orthogonal to the previous one. Also, if we get to a saddle point, stochastic gradient descent would stop moving, because the gradient at the saddle point is 0, and momentum would still have the momentum from the previous iterations and would still move and get out of the saddle point. This could also help move out of local minimas. There are two ways of taking the step using momentum. So we can choose where to compute the gradient. The regular momentum uses this equation we have seen before. Vk, which is the new direction to take a step in, is 1 minus beta vk minus 1 minus beta multiplied by the gradient at location xk, and then we have a regular update. The Nesterov momentum update uses vk equals beta multiplied by vk minus 1 minus the gradient at location xk plus beta multiplied by vk minus 1, and then we have a regular update. This is how it looks like. The regular momentum has a momentum step over here and a gradient step over here, and just uses linear combinations of the two using some beta that is a constant of the algorithm. Nesterov momentum update first does a step in the momentum direction, then computes the gradient over here, and then does another step. Another variant of the gradient descent algorithm is ADGRAD. Vk is equal to vk minus 1 plus the gradient at location xk squared. Xk is equal to xk minus 1 minus alpha multiplied by the gradient at location xk divided by the square root of vk plus epsilon. The square root of a vector, meaning take the square root of the entries of that vector. Raising a vector to the power of 2, meaning taking the square of every element in the vector. And dividing a vector by a vector, meaning divide element-wise. The reason we added the epsilon is in order for us to prevent dividing by 0. So we accumulate direction we have used already and prevent ourselves from going in that direction again. That helps us to reduce overshooting and the zigzag of the gradients. The epsilon prevents us from dividing. RMS prop. The problem with AdaGrad is that after some iterations, the accumulation is so big, it zeroes out the gradient completely. So RMSProp adds a decay to the accumulated gradient and this way tries to handle the problem. So Vk equals beta multiplied by Vk minus 1 plus the gradient at location xk squared for beta between 0 and 1 that is a hyperparameter of the algorithm. Xk equals to xk minus 1 minus alpha multiplied by the gradient at location xk divided by Vk plus epsilon. This algorithm combines momentum and RMSProp. So Vk equals 1 minus beta, Vk minus 1 minus beta multiplied by the gradient at location xk. And Uk equals 1 minus gamma multiplied by Uk minus 1 plus gamma multiplied by the gradient at location xk squared. And so dk, which is the steps we are taking right now, is equal to alpha, being the step size, multiplied by Vk divided by the square root of Uk plus epsilon. So xk equals xk minus 1 plus dk. We keep track of the summation of the gradients and the gradient squared and try to use momentum but try not to overshoot. So beta and gamma are hyperparameters of the algorithms and alpha is the step size. Here we can see a visual representation of all the algorithms. As you can see, Nesterov and momentum really overshoot because they have the momentum and the speed that they have taken from the previous iterations. We can see that SGD is relatively slow, goes straight, and then here, as it approaches the optimal point, it will start to zigzag. RMSProp is fairly fast, but it also takes very, very slow steps. Adam goes pretty much straight to the optimal solution. In here, it looks like Adam is slightly slower than the other algorithms, but in practice, we can see that Adam is actually one of the optimal and best solvers we have for optimization and training neural networks with a very big number of variables.